panel as a whole. Okay?
So after trying to follow that act, I'm not sure what I'm going to do here. Having adequate power and propulsion is a very necessary part of all these missions. Think of where we would be today if we had actually completed the nuclear rocket program. We had nuclear reactors. You wouldn't be talking about the limitations of doing these missions that we are talking about today. And in fact, we are spending a lot of time trying to make these sophisticated designs because of the fact that we don't have adequate power and adequate propulsion. Today's reality is that we're not going to really have another Apollo-type program. I think we've already seen that as the case. When we get the building blocks, and I think you just heard from the last speakers a way to use building blocks that are in existence, but we get other building blocks, we'll then be ready to go to Mars, and this will come about. So we need to think differently is how do we get these technologies developed either for the first Mars missions or for expanded Mars missions to accomplish the type of things that we want to do there. Understanding the past of what we've done, which is what I'm going to review briefly, is important to understand where we are and where we can go. Guess I can hold it. Sorry about that. Is that better? Okay, sorry. Anyway, understanding the past is, first of all, is vital to understanding, how do we get to where we want to go? And there's really three types of nuclear systems. One is radioisotope systems. It takes the heat generated from a naturally decaying radioisotope. Usually it's plutonium-238. And we use this heat to convert it to electricity. And these systems have worked very well in space, something like 33 years without failures on continuous system operation. So they're very reliable, and they have also proven that we can safely handle nuclear systems in space. We can get the launch approvals and things of that sort. However, the main limitations of radioisotope is the fact that they're only good up to a kilowatt or maybe a few kilowatts of power. This is because of they tend to scale linearly in the availability of the plutonium-238. The nuclear thermal propulsion systems were developed in the NERVA program and the rover program. These have been ground tested, but none of these systems have actually been flown in space. On the space fission power programs using reactors, the U.S. has flown one system, but it was back in 1965. The Russians have flown something like 35 systems. The biggest problem with the systems that we have are the lifetimes are too short for what we would like to have in the future, and so they need to be very further developed. Looking at the radioisotope systems briefly here, in the 1965, we flew the first system. It was a few kilowatt system. These systems have expanded out till we have flown almost a kilowatt system on one spacecraft. We've flown something like 45 radioisotope systems. None of these have had any failures in them on some 26 missions since 1961. The nuclear thermal propulsion systems, which the next speaker, Harry Finger, is going to talk about, he managed these programs very effectively, and that technology was developed from the 1955 to 1973. During that program, the highest power reactor systems ever built were built as part of the program. The highest temperature systems ever built were also built as part of that program. The specific impulse achieved is something like twice that of the chemical rockets. And since he's going to talk about it, I'm not going to go into much detail on it, but I want you to be also aware that the Russians had a very large nuclear rocket program, and maybe the combination of these two technologies would be something to look at in the future. The big thing is that none of these ever were actually flown in space. Here's a picture that there was a lot of hardware built. This is called the XE engine. It actually shows the reactors in that cylinder on the bottom. It actually has all the components of a flight engine in it. It took liquid hydrogen, used a prototype flight turbo pump to pump the hydrogen through the system. It was heated in the reactor up to temperatures like 2,500 degrees Kelvin, and it was exhausted through a nozzle at the bottom there. The nozzle was in a simulated space environment. The system was very successful in the operation. And one of the things to point out here is this program was started at a time when we were just bringing online the first small terrestrial reactors. So the technology to do any of these types of things did not exist. There were some 23 test articles built in the program, and it started out with research programs. We had to actually do the research to learn how you build a reactor at these types of temperatures. And from the research program, it then went into the engine development program, which is the upper part, which is the NERVA program.
I don't have to give a talk. You're giving it.
Oh, I'm not going to give the rest. But the biggest thing is, I'm taking as punchline, is that it demonstrated a reactor that could run for an hour at 2,500 degrees, and it also demonstrated that it could do it in a nuclear rocket configuration. Turning to the space nuclear fission power development programs, we had a lot of programs starting back in 1955, starting with the SNAP 2 program. SNAP was a space nuclear auxiliary power designation that was used at that time. That was to be a 3 kilowatt system, had a converter system using a Mercury-Rankine cycle, and the technology there were 2 reactors actually built as part of that and tested. These were 1-year systems. A spin-off of that program was the SNAP 10A, which used the same reactor, and the purpose of that was to get some flight experience to demonstrate the safety problems and what it took to actually fly a reactor, and that was successfully done. That was actually a 500 kilowatt system that operated at 810 K. It used thermoelectrics for a converter system. The SNAP 8, it was a 35 kilowatt system, and it was a Mercury-Rankine converter system. SNAP 50 was a bigger version of 300 to 1,200 kilowatts. while this was going on in this country, the Russians were developing their own systems. The Russians actually used them and flew 33 on what they call the Rorschach satellites, which were radar systems. These were thermoelectric type of systems. They also flew to that thermionic converter, which is the Topaz 1, and had an advanced Topaz system. In 1973, all these systems in this country, development was stopped. At that point, the Saturn rocket had been canceled. The reasons for doing a lot of these different things as a follow-on to going to the moon were terminated, and this was part of the consequence of our terminating that activity. In 1978, we were able to start a new small program called SPAR, which was a 100 kilowatt system, and it used a heat pipe reactor running at 1400 Kelvin. And as a result of that in 1983, the decision was made to go into the development of a 100 kilowatt. It was an industrial competition, and the SP100 program was formed. It had a 1375 K reactor outlet temperature and used thermoelectrics for conversion. This program continued for about 10 years. All the components for a flight system were demonstrated, but no reactors were built. In parallel to that, there was also some developments on thermionic reactors, and something there you see the multi-megawatt, which was for the Strategic Defense Initiative. They were studies for very short pulse type of powers. And these programs, again, were stopped in 1993. We keep starting programs, stopping programs, and then we wonder why we never get any place. Prometheus was to be an electric propulsion program with 200 kilowatts of power, and it went for about 3 years. They were going to use a gas-cooled reactor. They tried to use less advanced technologies. They tried to get away from refractory metals that were in the SP100 system. In 2007, they switched over to a 40 kilowatt fission surface power. And I should point out that the biggest enemy of success in programs is keep changing your targets. If you never keep to something and finish it, you can guarantee you can spend a lot of money and have nothing to show for it. And I think that's demonstrated when you look at this chart, as we kept starting and stopping things and never getting them finished. This was the one reactor that the U.S. actually did fly. The reactor is actually the little box on the top end. As you can see, it's a very small part of the system. The bigger part of the system is the cone shape there. The thermoelectrics were on the inside, and the outside is the radiator. And one of the problems you have in space reactors, why we try to build high temperatures into the reactor, is the radiator, because the only way you get rid of the heat is by the fourth power rejection. And so you want to get the radiators down to something sensible, so you make the reactor temperatures very high, and that makes the technology that you need very much more challenging. The SP100 is the 100 kilowatt system. It was all the components were developed. As you can see, the reactor in the lower, I guess the lower right-hand corner is a very small part of the system. It's followed by a shield which protects the payload. You notice how they're shaped is to keep the payload in the cone angle of the reactor. There's also a boom there to minimize the amount of shielding so that your radiation to the payload is to an acceptable level. The conversion system here again is thermoelectrics, and the wings there are the heat rejection system. The system was designed to operate at 1375 Kelvin, which required refractory metals. And you can see that this system weighed 4,600 kilograms. With some further optimization, when you can get it down probably to 4,000 kilograms. But when somebody talks about making a 200 megawatt system like they were talking about yesterday in electric, you're talking many, many football fields of just radiators, and you're talking weights that are just outlandish. These have been very well optimized to get down to these weights. The Prometheus system was they decided to try to, this was going to be a 20-year life system. And a 20-year life, they decided to try to use technology that was much simpler, closer to terrestrial experience. So they, it's a gas-cooled reactor, lowered the temperature to 1050 on the reactor temperatures. They used a Brayton cycle converter, probably, or it could be used as a Stirling cycle. And the current system that they're working on components on is a fission surface power system. It has two configurations. You can see one they call a landed configuration. In the landed configuration, everything is a unit. You just put it on the surface and land it and string electric wires out, and then start to operate it.
Who was working on this?
Let's see, I think it's Savannah River is doing some of that. I'll tell you. The emplacement configuration is that if you have the capability to prepare a place in advance to put it, then you can use the regolith that's there, and you don't have to take as much shielding with you. And so the emplacement configuration is about 40% lighter. And this looks like very much like, in many ways, like a terrestrial reactor. The red there shows the fuel elements. It's a uranium dioxide fuel pin, very similar to what you get in terrestrial reactors, with stainless steel cladding around it. The blue around there is cooled by NAK, N-A-K, for coolant. The outside is surrounded by a beryllium reflector, and it's in the form of, the reflector has drums. There are 6 of them there. The drums have what they call a B4C. It's an absorbing material. And the way you control these beasts is just rotate those drums around to control it. The large blue area represents shielding. If you brought it into a landing, this shielding you'd bring with you to protect people. So this quickly summarizes the state of what the technology is. So how do we get this technology developed so it could be used on Mars missions and other missions? And to do this, we looked at what are other missions that are synergistic to what we would like to do. Where would this really help out? This is part of a NASA mission set. The most demanding would probably be the Pluto orbiter there you see at the bottom. If all we want to do is flyby missions, you can take a nuclear rocket of the technology that's already been developed and use that, and you can get the payloads that you would want to do. And we looked at something like 5,000 to 25,000 pounds of thrust. Something like a 15,000 pound thrust engine would do a very nice job. And one of the things nice about a 15,000 pound thrust, we're looking at systems that could be launched on something like a Titan IV, an existing launch vehicle, to do this type of work. And if you took 4 of those 15,000 pounds, you could then do the Mars missions that you would like to do. When you talk about orbiters, this is a little dizzy, and I apologize, but if you just look at the Pluto is fine for using the nuclear rocket, but you can see that on the corner here that if you want to do orbiters, you've got a problem. So there are various types of combinations you could consider. You'd like to minimize your electric propulsion times because of the reliability and the time it takes to develop a system. If you took say like an SP100 system and you did it 8 years of propulsion, it would take about 14.5 years to do the mission. Doing it all with just nuclear power, nuclear thermal power propulsion, couldn't quite do this. And then they have various combinations, and I think I'll just skip over, but the best combination really is to do a separate nuclear thermal rocket and combine with a nuclear electric propulsion where you jettison the rocket after the first part. And this would enable you to do the Pluto type of missions. All these other missions that we're talked about are also enabled, but it also gets you the technology developed and the experience that you need for doing Mars type of missions. So you heard earlier about thinking differently, the transcontinental railroad. I think we need to start thinking differently also on how do we get the nuclear systems, get the systems that we're going to need, the power and the propulsion to do these future missions. And with small nuclear rockets, we could greatly expand the exploration to the moon, to doing outer planetary missions, and then we'd have the capability for doing Mars missions. For fission power, again, it would, if we could get these systems completed for other things, we would then have adequate power to do much more on the moon, which is what you would like to do, because we're going to, we don't want to just go to the moon to put people there and show the flag. We want to really expand and have settlements, and we're going to need a lot of power, and power is going to be a very restrictive thing. I want to emphasize, though, that we have a lot of experience to build on, but we shouldn't ignore what's happened since that experience, that there's been a lot of developments in computing, materials, converter systems. So I think what you want to do is be aware of what's been done in the past, build on it, but also be aware of what has evolved since then. So in summary, understanding the past is important. We need hardware-rich programs. The most successful programs that we had in space power, and I think this is true in others, where we had a lot of hardware built in the NERVA program, in the SNAP programs where they built a lot of hardware. They ran 6 complete reactors in that time. And these, no matter how much you analyze things, you have to actually go out and do it. Thank you.
My turn.
We gotta switch you around. I think we have the technology to do it, to do that. The the question of how much.
How much and how long?
Unfortunately, we have actually destroyed most of our capability.
Yeah, I know.
So I don't really know how to answer it, because we would have to.
The PDF?
Good.
That really is the answer, is that we have to reestablish that capability.
Yeah.
Okay, and it's not going to be exactly like it was before.
Of course
because
not.
A lot of the test facilities
You're not going to be able
is
to
not
test
there.
it
So,
in the open air.
right, we have to establish some new testing capability, and that's what I'll talk about.
And how big a launch platform? How big a system do we need to launch if we're not going to do any assembly?
Well,
In orbit, docking, but not assembly.
No.
Wait a second, let me get it on.
Well, this is one of the reasons we're talking about the 15,000-pound thrust, is your facility requirements go way down. How much, how big a facility. Actually, they have tested a closed-loop system. It's already been shown how to test it without exhausting into the atmosphere. So that the technology exists. It's really a question of reestablishing it. With the 15,000-pound thrust engine, you can you simplify a lot of your developments, the size of facilities, et cetera. But unfortunately, we have to reestablish the hot cells and other things. And I guess I could give you a number that I would consider worth anything.
15,000 or 15,000-pound thrust. How much? How big would the equipment have to be?
I'm going to get into that in my speech after the next one.
Okay.
Slide one.
But the focus that we had in the development testing out there was really focused on at least 100,000 pounds of thrust out of a 35-inch diameter core, 52 inches long. And we did the one test that got up to 210,000 pounds of thrust, and it was a complete success. So the capability is there, depending on what you want to do.
Well,
15,000-pound engine would thrust
it'd
with
be nice.
2,550 kilograms.
It'd be nice to be able to push a Falcon
So you join NAC in
Falcon
1944,
I was
joined
in NAC.
heavy
Right.
payload to Mars with
Okay. All right, we're going to get going on the next speaker. It's a special treat. This is Dr. Harry Finger. Harry joined NACA, the predecessor organization of NASA, in 1944, and then became an important part of the NASA nuclear rocket program starting in 1960. Shortly afterwards, ran the nuclear NASA. In 58. Okay, sorry, because I only became aware of him in 1960. Anyway, and basically was in charge of NASA's space, nuclear power, and propulsion programs through the 60s, through this incredible NERVA program that you'll hear about today. So, Harry Finger.
Thanks very much, Bob. Let me tell you, I'm a little wondering about why I'm really here in view of all the new things that have been presented in this discussion, including the detail that we already have about some of the Mars environment, which is just fantastic in my mind, and the ideas that Bob presented on advanced ways of really moving forward in a really flexible and strong way to explore into Mars. And somebody's got to start setting some goals in that direction, and that's the thing that has got me most upset, and I have to admit that that's the point I've been making for a heck of a long time, because I had the feeling way back by 1970 that we had a capability to start developing to go to Mars and do some real exploration. And the program that we had developed was cut off. So that's what I'm moaning about. But I'll give you some of the insights into it a little bit. Sure, a lot of it is personal because that's the way I still feel about it, but I keep emphasizing the point because I have felt all this time over this past more than 40 years that where the heck are we? And it's about time we started moving. And I therefore welcome terrifically the work that Bob Zubrin, the Mars Society, and all of you have been doing to try to get us back on track and get an emphasis on it. I get a little bit of a hint that there may be some slight growth of it. But it brings me back, frankly, the situation that was mentioned, I don't know who mentioned it, but earlier today, I can't recall who mentioned it. But President Kennedy gave a major speech back in, when was it? 61. He gave a major speech, special message to the Congress on urgent national needs. And in that speech, his major proposal was, and I'm quoting now, that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to Earth, unquote. And he emphasized all that would be required to accomplish it in that situation is that all of us must work to achieve it. And that's the goal I feel about this. But the important thing is, his second proposal in that speech was, quote, accelerate, I'm going to read it precisely. I had written all this out, but I don't want to be quoting from it. He specifically said his second major item in that big speech was, quote, accelerate development of the rover nuclear rocket. This gives promise of someday providing a means for even more exciting and ambitious exploration of space, perhaps beyond the moon, perhaps to the very end of the solar system itself, unquote. Okay, so where are we? We developed the capability to go to Mars, and we quit. And that's the thing that worries me very, very much. And that's why I say, look, let's get the program going again. Let's get a joint office, such as the one I headed for the rover NERVA program, and get the Department of Energy and NASA together and say, let's move and get this country back on track to do exploration, to do advanced work, to stimulate our people, to encourage all of our community, the scientific groups, the engineering groups, the companies that were involved in our program, to get going and really stimulate all of that. So we also reestablish, I might say, or maintain our leadership in some of these areas, which I'm very concerned we're losing as other countries move quickly ahead. And the way this started, frankly, I was almost a young punk, I guess, back then, when NASA was established. And the Air Force had been working on nuclear propulsion work for missile application. Principally, it was an AEC Air Force activity going. And when NASA was established, President Eisenhower issued an executive order transferring that program to the new NASA. And it was a controversial thing. I got involved immediately as the point man for NASA in that activity, but the head of NASA negotiated with the head of the AEC, and that got a little controversial, and then the congressional aspects got a little controversial in the whole thing, and trying to get it set up. Okay, it finally went through. That was in October 1 of '58, as Bob has mentioned. But NASA got that job, got that assignment, but it was October 1 of '60 that there was a memorandum of understanding, and I was named at the head of it as the head of the new joint office, and Milt Klein, who you may have heard about, was named as my deputy. And the fact is, my real problem, as I've indicated, is we developed what we really intended, and we got nowhere from there. There were significant parts of the program, and we got in October 1 of '60, and here are some of the things, the early actions that we started. We stepped right up and very fast, brought Aerojet General and Westinghouse in to head the development of the rocket engine. Almost immediately, we put out the proposal requests and went right to work on that. We also decided we better have a capability for flight tests. So we got Lockheed to develop what we call the reactor in-flight test system. We went ahead then and expanded the test facilities in Nevada, because there was only one test facility for reactors at that time, because the Los Alamos laboratory had been working in this program in the 50s, earlier 50s, and as you can see on this one, their first reactor test was this one. They actually had 2 reactor tests at that time. 2 Kiwi A reactors at that time. They ran at about 80 megawatts of power. And then there was a third test run in October of '60. Yeah. Ran at 100 megawatts of power, and each run ran with gaseous hydrogen, water-cooled jet nozzles, and they ran for about 5 minutes in that one test cell that was there at the Nuclear Rocket Development Station. And the team running Los Alamos, I have to tell you, was really terrific. And they're shown here, some of the old timers, and I'm afraid, sorry to say, well, in the background is Norris Bradbury, who was the director of Los Alamos. Next to me on the left there is Raymer Schreiber. Then in the middle there is Frank Durham, who incidentally is the only one of those old timers that is still around. Then there's Keith Boyer on the right, and Rod Spence next to Frank Durham in there, and there are the 2 young, the third from the left, second from the right. I can't remember their names, but they were part of the young test group that we had. They were terrific. There's just no question about it. And we came, not only worked together closely, lived together, but we were friends all through that, with the families and everything else. And it was just a fabulous relation. I'm expressing personal activities now. But we then got to what was really what we thought was the super design. They moved on through those first reactors, and they were designed and designed for 1,000 megawatts, 50,000 pounds of thrust. And we got to this Kiwi B4A reactor that we thought was the reactor. Absolutely terrific. We put that on test. They had niobium carbide protective coating on the graphite fuel. All the fuel elements were graphite. I think you all know it. I hesitate to go through this history because I think most of you who are here already know this history. I'm not sure why I'm going through it or why I'm even presenting this to you again, but you've heard it, and I'll give you a little, maybe minor insights into it. And this was really the preferred design. It was put on test November 13, 62, and man, we expected this is the reactor that was going to be it. We put it on test, and flashes of light in the exhaust nozzles immediately indicated core damage. As the power went over 250 megawatts, and in just a few seconds we shut the thing down. And we thought, oh boy, where are we now? And then a week later, after our failed test, just a week after that, on December 7, 62, President Kennedy and Lyndon Johnson visited Los Alamos and then came to the Nuclear Rocket Development Station, to the test site, to visit the test site and look at the test facilities and get a report on the full program and everything else. A week after we had the major failure. And there you can see a whole batch of the people. Glenn Seaborg from the AEC, because we headed a joint office of NASA and the AEC. Bob Siemens, second from the left, who was the associate administrator of NASA, and various others, a whole batch of people who were there. Associate, and Milt Klein is over on the right with the glasses, way over, my deputy. And people who were in all of these areas. And what we got there, frankly, and I already indicated what the president had said before that, of his support for the program, and there was no question when he visited here, he was interested and really wanted to do it. The only one who had seemed to be very sour on it was Jerry Wiesner, who's on the left here, who was his science advisor, and he kept asking questions. Why do you want to do that? And things of that type, indicating criticism of the whole reason for going with nuclear propulsion in the whole system. But we moved forward with it nevertheless. But needless to say, when the president left, I figured we'd better find out what the heck happened to us, because it was on our mind. We didn't even know what the heck the explanation was for it. So after that gathering with the president, I called a meeting of Los Alamos and NASA centers and various other people to go over it. But I said, look, let's quit the testing. Let's figure out really what the heck happened. And I remember Norris Bradbury, who I showed you on the previous chart, said, you'll kill the program if you don't test. And I remember saying to him, we'll kill the program if we keep testing and fail. And I said, no more testing. Let's go into the component testing. And we went through all kinds of component testing. And I said, let's just do a cold flow test through a reactor. That immediately revealed what the problem was. And there was one time when Los Alamos had really goofed, because they had put the peripheral seals of the reactor at the inlet end. So there was a low pressure around the whole circumference of the darn reactor. And needless to say, the fuel elements vibrated and cracked right out. It was a goof. Well, we got that fixed pretty fast. and we moved on from that. The interesting thing is Westinghouse had been working on trying to increase that peripheral containment in the reactor right from the beginning. Not only with exit seals, but really with full containment through the whole reactor, not just one section or the other. So goofs occur in all kinds of situations, even with a brilliant outfit like the Los Alamos people, and they were terrific. But this is the kind of test program we had. The Kiwi D4A, you can see where it is in '62. We then went ahead with other testing. And there's just no question. Los Alamos went ahead and then went into the Phoebus testing at 4,200 megawatts of power, 200,000 pounds of thrust equivalent. And I think, I have to say, I think Dave has given you a terrific summary of much of this work and of all the work that we've done in this area. I really think it's just outstanding. And then we had a Kiwi, let me see, where was that? Aerojet and Westinghouse did reactor tests. They started in '64, and they had one reactor test in the NERVA NRX tests that ran for 62 minutes at 1,100 megawatts in '67. A full hour at full power, no problem. We were really ready. And then the picture that Dave already showed you of the XE engine. That engine, over 50,000 pounds of thrust, set up in a test cell that we had built when we took over. It ran for 4 hours with 28 starts, with no problem. We were ready to go. And our earlier proposed flight test program had been killed by that time. It had actually been killed in '65. So we had no flight test program, and the whole program was ended in '69. That ended it. There's just no question we developed the capability to move well beyond Earth orbit. We had to move forward with it. We could have done it at that time, and we would have been there if we had proceeded, but the program was cut off. Now my question is, let's go to retrieve it. And as you've heard in this meeting, and I think it's really been very helpful and demonstrative of how much new technology has been developed, new ideas have been developed to expand what we showed we could do back then. And it's hard for me to feel comfortable saying, oh yeah, well wait 25 years before we start talking about a Mars mission. You know, I have great difficulty with that. And I think that's the area in which I think Bob Zubrin, the Mars Society, and many of you who've been here and talking about it really what I feel also is we have to keep emphasizing, let's get going on to Mars and building a capability for it. And not with picking a variety of things to work on, but let's say, what is the mission we have? And let's aim at the mission. My problem is, as I think to some extent you've indicated, Dave, there are all kinds of ideas out there. But if you don't have a mission, you're not focusing it. And you're not really aiming at a particular achievement that can prove the development of that capability. So you wander around, you don't really put the effort into it. So let's get going and start thinking of what we did, use that, but we can advance it far further with the technology that we now have. Oh, I should have mentioned, I skipped it, but here are some of the payload benefits that we had done with the nuclear upper stage on a Saturn V vehicle. They're obvious, 50% increase. Here's a Mars mission, manned Mars mission, with Earth orbit weights for the manned Mars mission at various launch years. The benefits are very clear. Let's go with it and move on from that with the advanced technologies that we now have. Thank you.
One of the first points I wanted to make on this is that the start of the concept of a nuclear thermal rocket goes way back into 1947. It was at that time that the scientists of North American aviation, after examining the possibility, proposed that hydrogen be used as the fluid, propulsion fluid, and it be heated by a nuclear rocket propulsion system. And that resulted in, first, some early interest in being supported by the Air Force in getting started on this. And I was involved in interacting with the people at Martin-Patterson Air Force Base in Ohio, and my close friend Charles Trent of Aerojet and I put in quite a bit of time trying to get their interest in what could be done. But then things changed, and NASA was created, and then we started moving on the program itself. The chart that you see up here before you is a category of all of the Kiwi down through the NRX and the nuclear furnace tests that were conducted in the period of time from 1959 to 1972. The start of the reactor tests to be used with liquid hydrogen, but it was the first 3 tests were run with gaseous hydrogen, was the Kiwi A experiments. They were short, fairly short, and they were run at between 70 megawatts and 100 megawatts, but they were successful in demonstrating that it was possible to heat a propellant like gaseous hydrogen up to a good exit temperature, even though that the power level was only about 100 megawatts. The real testing of the fuel elements at the higher power level was based upon an assumption of a desired production of about 1,000 megawatts, and led to the testing that we ran on from 1961 up to 1964. Those tests used the initial version of the carbon fuel elements and demonstrated that there was the potential to operate at a high enough temperature to realize the real interests of NASA in a possible propulsion missions. At the end of that time, those tests were conducted by Los Alamos and used a liquid hydrogen feed system and nozzles produced by Rocketdyne. At the end of that time, it was apparent that NASA wanted to move to an improved, higher capacity capability of reactor. And so they started focusing then on what later became known as the Phoebus reactors. But with the initiation of the planning for that, the Aerojet Westinghouse team took off in 1964 on the development testing in Test Cell A of their reactor concept, which worked out quite well. Then came a decision, or the results of a decision, made by Los Alamos to improve the capability of the reactor core so it was possible to design the coolant flow through the core in such a way that one could make a change and not have to go with the bleed cycle, and that's resultant impact upon the performance, go with a topping cycle, expander cycle. And with that decision, then came the decisions to work forward on improved reactor and propulsion system capabilities. That resulted in a variety of tests ranging from initially 1,500 megawatts out of a 35-inch core we had, and then shoving it on up to a higher level, and then running a larger core, which was a 55-inch diameter core that went out clear. It was targeted for 250,000 pounds of thrust, or 5,000 megawatts. And the very first test out of that, we got it up to a power level of around, equivalent to around 210,000 pounds of thrust, 4,100 megawatts. After that was accomplished and successfully demonstrated that if NASA wanted something that big, they could have it, then the interest went down to a smaller size core to see what could be done at that level. That shifted down to a 20-inch core, which was called Pee-wee, and that was used in the next series of tests. But while those tests were going on, the Westinghouse Aerojet team was then preparing for and then conducting a successful series of tests on their engine in parallel with this other activity. Then finally, after all these tests were over for the time being, which included the XE prime engine development testing out in a different test cell, then a decision was switched to a new kind of propulsion, which would be the nuclear furnace. But before I get into that, let me just say a couple words about the XE prime. That was a very successful application of engineering activity to provide the capability of being able to conduct a range of operating conditions successfully. It is remarkable that this was done, but if any of you have any real interest in seeing some more details of that, be aware of the fact that there has been produced on a television series several years ago the testing activities associated, or rather a picture of where the tests could be conducted and how the test facilities were designed to do that. That series is called the Mars series 1, 2, and 3, and I was fortunate in being selected to be the person on television that explained to the people just how that particular test facility was constructed and what it would do. It gave me a lot of pleasure to be able to do that. The last test was this test on the nuclear furnace, which was a step in the new direction, which is to be able to go to a higher operating temperature for more advanced performance. And that was called the nuclear furnace, which was used to demonstrate that it was possible to have two kinds of fuel elements within the core in order to be able to produce this higher exit gas temperature and an ISP that would be up to around better than 1,000 seconds rather than 900 seconds. And with that test conducted, that was the end of the testing that was done. Now I'd like to shift the discussion to, given this as background, what are the doors that are open to us, or routes to take, in order to give the manned Mars mission people planners good, accurate information on the performance operating characteristics for such a NTR engine. The first point I want to make is that it's possible, with the advances made in the program that I've just described, to go for a higher performance system. And that system would make use of what I've previously discussed, was a topping cycle, expander cycle engine, rather than a bleed cycle, because the bleed cycle engine has a penalty to get the power through the turbine. The use of this kind of an operation involves the planning for how we're going to get to the operating temperature conditions. What I'd like to show now is the capability of my next chart, which I indicated I could just punch this button, but it doesn't seem to work. Who's the expert?
Enter.
Let's try this one. Let's try this one. Let's try this one.
Let me have stand in your way.
Let's go. Page down. Sorry about this.
There we go. Oh, no, that's not it. Next one.
Oh, there's only one page here. Okay.
Yeah.
Gotcha. So you want this?
Go ahead, show me.
Okay.
What are you pressing?
I'll just open it up.
Yes, that's it.
Okay.
That's fine. That's the one I ought to use.
And I'll give you full screen. All right.
Okay. The first chart on this particular phase of my discussions are based on the assumption that a Mars NPR propulsion system could really benefit from using a nuclear thermal rocket engine that could produce 100,000 pounds of thrust. And its performance would be then to be able to give over 900 seconds of ISP, which is over double what the best you can get out of hydrogen, oxygen chemical engines. The work that we did out in Nevada proved that we could have such an engine without a shield and still get adequate performance. That meant that the maximum weight would be less than 18,000 pounds. Further, we could have a full performance operating range at full thrust from all the range from 50% on up to 110%, right at the full temperature. In the event that there was a problem with the propellant feed system, there was a capability of using, since we're using 2 turbo pumps, that you could cut 1 pump out of the system and still get up to 70,000 pounds of thrust from that 1 pump. Further, we made tests late in the rover program of advances in the turbo pump. And the turbo pump we focused on was the one that gave the smallest size, the lowest weight, and the highest performance, which was a axial flow turbo pump. And that we were able to show that by modification of the inducer, we could take a situation where the propellant tank wasn't pressurized, but was at saturation conditions. And under conditions of that, the flow of the hydrogen out of such a tank down to the pump ended up with having as much as 30% vapor created coming into the inducer, and yet within the first portions of the inducer to repressurize that back to a solid liquid. And it worked very well. We also looked at the requirements of operating for 2 hours, with having a number of restarts up to 6, and having a transition from the initiation of flow to full thrust of 30 seconds, and a transition from 50% thrust down to cutoff of 30 seconds. And the maximum core temperature and the afterheat after that was 1,800 degrees R. Next slide, please. Where'd you go? Yeah. That's all I needed after that. Okay, fine. This particular chart shows you that for the design of that engine, in determining what sort of expansion ratio you want to go onto the nozzle, if we were going for 4,860 degrees R, which is right about in that level right there, we could go for an expansion ratio by going as high as 500 to 1 and get the specific impulse of 920 seconds. And that's what the capability of this particular probe is. Now, where'd you go? You hit this button? Yeah.
This one here.
This one there, okay. The design of the flowing system for an expander cycle operation has two options as shown here in the diagram. The one we picked was configuration B. And here, as you can see, a portion of the pump flow comes out, goes down through this assembly of the combined units in there that have 6 fuel elements around the tie tube, picks up enough heat without going through the elements that heat it up to the full temperature of the gas, but in between that, picks up enough temperature to go on up and drive the turbine. And there is also flow that is cooling the portion of the nozzle section and then on up through the reflector and down through the core that is picking up some heat here also. This gives a outlet temperature of the gas coming out, which is right up to the full temperature of the gas temperature being generated. In other words, we don't pay any penalty for having a bleed cycle. We're right up to full performance with that. Here's a very limited view of the assembly of the core. This is a 35-inch core, 52 inches long. In this particular design, there is a capability for having these sub-assemblies of being able to look at the output of 6 fuel elements per unit of inflow. And we have the actuators that drive them. We have a top reflector, and then the actual fuel elements themselves, which are designed to have a 3/4 inch across the flats, 6 elements across, and have 19 fuel elements, each one having a hole of around 1/10 of an inch down through it. There's another consideration on the design of that engine, and that is the actual amount of temperature rise that will occur in the uncooled portion of the nozzle, a high expansion ratio. And for a 500 to 1 expansion ratio nozzle, as you can see, the wall temperature is down below 2,000 degrees R. But as you work your way back for less and less expansion ratios, area ratios, you start climbing and get back very far, you'll get over 3,000 degrees. So part of the optimization of this system is to have a uncooled portion that gives you the expansion ratio you'd like to have, providing you have enough space below the reactor core itself to provide the capability. Here is a picture of the cooled, uncooled assembly itself with the dimensions shown. This is the cooling with tubular cooling. This is design of the converging wall section of the cooled, total cooled portion of the reactor assembly. And then you go from that to this expansion ratio of the uncooled portion that you have the option to go and clear up to 500 to 1. Okay, I'll try to shorten this out now and move on to the next. This is the picture of the turbopump nozzle that I showed you where the expansion ratio we worked with that and get what we wanted. Here's a picture of the control system used. The main thing that we got was the temperature sensor and the pressure that we needed to control by the rod controls. And this is the actual heat generation after shutdown that we have to concern ourselves with in providing extra thrust. And here is a picture of the actual fuel, the actual mechanisms that are used in the control system. And here are some more pictures of those components. And this is the final version of the reactor assembly with its liberation of the uncooled portion, the cooled portion, the reactor, and then all the feed system and control systems. And here is an actual setting down here of the operating parameters at various points of operation in the system. Need some help with this. It's my page. Next, I'm going to go on to the next one.
Gotcha.
Yeah. Okay. That's fine. Here, take it from there. That's what I wanted.
You want to see it like this?
Yeah, that's fine. Okay. Next subject I wanted, and the final subject I wanted to talk about, was making a further advancement in the capabilities of NTR engines to be used for the kind of missions like the manned Mars missions by going for a little higher performance of the system. And start off by being able to point out that the graphite fuel elements that are used, when it was before totally, was limited to about a propellant maximum temperature of 2550. When we got to the composite fuel elements, it was 2650. But if we make use of the capabilities of the all-carbide fuel elements, that could get us up to 3100 degrees. Now this is a picture of having a reactor assembly, a single assembly, where the first 3/4 of its length, down to about 42 inches in length, would be in this case, the design, the lightest form of fuel element, the carbide fuel element. Then the next phase would be to use a carbide fuel element that would take it on up to the maximum 3100 degrees operating conditions. To affect this transition between the graphite and the carbide, there's located in the design a 1-inch thick adapter flow condition that can stand the temperature but redirect the propellant flow from the fuel element holes that come through the graphite element, which are around 19, up to the number of fuel element holes that are in the carbide, which is about double that, about 37. This is a tabulation of the pressures and the temperatures of the various portions, and it shows where there's complete commonality, where there's a change by going to the operation where there's a graphite initial 3/4 lengths and a carbide portion, the last 10 inches, to provide the exit temperature of 3100 degrees Kelvin. Here's a picture of the reactor from that. It looks very similar to what you saw earlier, except that the lower portion of the reactor, that 10 inches, is down at this level. The rest of it, the higher, coming from this level down, is on the lower temperature of graphite operation. This points out an issue of the benefits that are obtained if you add an axial reflector at the top of the core rather than having a reflector only around the core. Because if around the core you start at a lower level and you get to a higher operating temperature, whereas you take the other case, you come up immediately and gain all this heat transfer taking place in that area, and it really helps you. This is a drawing of the parameters that would exist in this expander cycle. Here is the parameter, it's the characteristics of the engine. 100,000 pounds of thrust out of the same diameter core we've been talking about for most of the presentation here. Specific impulse of about 102 seconds, excuse me, 1,002 seconds. And the masses of the different assembly leading to a reactor assembly, which are not too much heavier than if it had been the graphite system to start with. The rest of the engine system is shown. The next heaviest is the nozzle assembly, then the dual turbo pumps, which is the smallest and lowest weight, and then the propellant lines and the controls. And here's a picture of the actual engine system. Over 1,000 seconds of ISP and very, very high efficiency. Yeah. I think I'm done.
Savannah River site. I work for Savannah River Nuclear Laboratory. I'm the junior member of the panel. I only have 4 decades of experience in nuclear facilities, starting with a nuclear submarine. And with my luck, it was a Thresher-class submarine. So I learned that reactors break. So one of my lessons learned was be prepared for when things go wrong. A little bit more information about Savannah River site. It is big, 300 square miles, and it will fit inside the beltway of Washington, D.C., which is a good thing to be prepared if something goes wrong. And we're located in Aiken, South Carolina, which is right across the Savannah River, central Savannah River area, right across from where they play the Masters golf tournament. Which means that DOE headquarters, our DOE facility, wants to visit us a lot, especially around April. At one time we had 5 operating reactors producing nuclear materials. I think David alluded to the fact that many of those were produced at Savannah River. The plutonium-238 that's in Cassini now and Voyager, as well as nuclear fuel for SNAP. Now we have 2 totally decommissioned reactors, R and P reactor, and we have 3 CL and K that are deactivated from former weapons production functions. We've got several areas that I work in A area, for example, where the laboratory is. We have fuel fabrication laboratories and shielded high-level cells, which are very important in doing testing. We have an H Canyon and tank farm facilities, and we have facilities to immobilize any nuclear waste. The laboratory was established in 1951 to provide research and development support for startup and operation of the reactors and its mission to produce nuclear materials for national defense. And we serve the Department of Energy, the nation, other federal agencies across the country and around the world in 3 areas. First and foremost, we are the lead environmental management lab. Some of the cleanup technology we've developed is being used at other DOE complex facilities. I'm in constant contact with Japan on the Fukushima effort. A lot of the technology, I just brought a couple posters and one of my toys, advanced silicon carbide filter, is being used in Japan, as well as Russia and other countries. And we also have an immobilization facility in the Defense Waste Processing Facility where we take high-level waste and turn it into a glass monolith that's qualified for storage in Yucca Mountain if it ever gets built. Right now we call ourselves Yucca Mountain East because we have about 3,000 canisters of these things ready to go. So we are Yucca Mountain East. We also have a national and homeland security mission. We're involved with tritium technology, which is a radioactive form of hydrogen. You heard Robert talk earlier about the deuterium on Mars. Well, there's tritium around as well. We also have nuclear materials technology supporting the disposition of plutonium and spent nuclear fuel in the form of what's called MOX, which is a mixed oxide plutonium and uranium, which we're taking weapons-grade material and we are turning it into commercial reactor fuel, so we're burning it up, which was the ultimate for weapons to plowshares. We also have a homeland security function. We do nuclear forensics for the FBI. We do a lot of non-proliferation work as far as nuclear monitoring and detection. And we're involved in biological and chemical collection technologies for non-proliferation. wanted to go on and talk about how did we get involved in the space program. I think Robert may have seen me involved in some NASA functions. One of the proposers for the crewed exploration vehicle on the associated with Beyond Constellation selected us to support them with technology development for nuclear propulsion, and our proposal was rated very highly by NASA as technically superior. We responded with the proposal to the bimodal concept, as well as to develop testing facilities to support this. Now, this is non-trivial. The testing facilities that were available for NERVA are no longer available. So we need a big facility with an infrastructure that can handle the needs for doing thorough testing. Well, as luck would have it, you heard Westinghouse was involved in the NERVA program. Well, they won the bid to operate our site back in 1989, and they brought with them 600 engineers who were accessed from NERVA and a whole slew of aperture cards. So they have a history associated with the U.S. nuclear rocket program. This is a different picture with Kennedy at the Nevada test site, where he's actually between a couple of the tanks that were out there. But basically, you don't have that one?
I'm in that one.
Oh, you're in that one. I figured. I was also going to mention that Glenn Seaborg, who was in your other picture,
Yep.
he discovered the neutrino at one of our reactors at Savannah River site. So he didn't just do the rocket program.
He was head of the energy.
Oh, yes. And this is just a summary of the accomplishments. 4,500 megawatt thermal power, 250,000 foot-pounds of thrust, 90 minutes of burn time, and the thrust-to-weight ratio, which is critical in planning your Mars direct mission, was between 3 and 4, which is still substantial. It's good benefits. The status of the NTR ground testing, well, those facilities are deactivated and they're reassigned to other functions and just not available. Now, there was a NASA subpanel final report evaluation that said also that those rocket test cells, the cost of refurbishing and putting those back into service would exceed the cost of new facilities. And they're obviously degraded. Their presence right within the view of the Yucca Mountain test repository is kind of going to be complicating the NEPA review if you ever try to use it as a test facility again. Well, basically what I'm here as an epilogue to say we don't have those facilities anymore. We need some new facilities. NASA has already been evaluating several new facilities with several of the DOE complex facilities to see if they're eligible for use as a test facility. And there's some emphasis here about what the assumptions were in that panel. So here's some additional considerations concerning Savannah River National Lab and SRS. They'd evaluated us as an acceptable test facility before for space power systems, up to the full-scale ground test. I know I'm too tall to go to Mars, and I eat too much, but that's one thing the nuclear Navy did. They fed us very well. SRNS is currently disposed of excessive highly enriched uranium, which is what we were calling HEU. by downblending for commercial reactor fuel. And so we have access to that material. That's very important because not all laboratories have that. We've demonstrated success in fabricating fuel for the U.S. Navy and for our production reactors for decades, and the space fuel. And we are in possession of a metal hydride technology for hydrogen purification and storage capacity. And we've completed testing of a standby gas treatment process using the silicon carbide labyrinth design, which is capable of standing up to very high temperatures. We're planning on using it on our waste tanks, and now it's being used, well, throughout industry for high temperature applications as well. It has a very low pressure drop across it. So we have the capability of using a state-of-the-art standby gas treatment system. And we have high-level waste tank storage and processing for mobilizing any debris, like from the failed fuel that happened during the NERVA program. So we have a full range of infrastructure capable of supporting the test program. Some other open cycle requirements include, besides the effluent treatment system, we have safety class sand filters. Now, part of what comes out of failed fuel is you get fission gases, which you can get some iodine, you've got all kinds of xenon, krypton, and those sand filters hold that up. I think there's one about 300 foot from my office. Not that I do any testing in my office, but it basically covers the whole lab. And every one of our nuclear facilities has that. Now, other DOE complex facilities don't have those safety grade sand filters. So that's an important consideration, especially if you have people who live on the other side of that site. You want to make sure that there's no chance of any contamination escaping, should there be some. We have all kinds of, they were tested, by the way, with radioactive tracer gases. And we have prior studies that had like 60 pounds of pressure up against those, and they work very well. In fact, there's several, like I said, high-level waste treatment facilities using those silicon carbide systems now. We have a full-service fuel fabrication laboratory, and it's staffed as well. We have the shielded cells. We have some state-of-the-art fuel fabrication capability. We're involved with the advanced fuel cycle as far as nuclear power operations are concerned. And we have some additional testing capabilities for hot hydrogen propellant testing. I was under contract to NASA Stennis. NASA Stennis can't do any nuclear testing, so they asked for conceptual designs, and I supported NASA Stennis with the design for that. We can also do a lot of hot hydrogen flow testing, and we can work in conjunction with the other DOE complex laboratories, like INL. I just got back from the Advanced Test Reactor. So we're so understaffed compared to what we were in the days of NERVA that we really work closely together and collaborate well, and with Los Alamos as well. So we have some additional irradiation facilities, test facilities at the Advanced Test Reactor we can use. And we can use the existing structures, even though they're deactivated, as CL and K reactors, because they were rated for handling 2,800 megawatt thermal power. And we had infrastructure to support getting rid of that heat. So we can do prototypic fuel element and NTR ground testing. This is just a diagram of this is right out of one of those reports for a modification using the hydrogen metal hydride beds. Those are great for storing hydrogen. we showed, to their satisfaction, NASA was very interested in that they had like 3 barges full of hydrogen at NASA Stennis, and one tended to sink during Hurricane Katrina. Whenever I showed them that, you know, we could store a lot more hydrogen in these metal hydride beds, they were very impressed and said, oh, we could save the taxpayer a lot of money with this. So again, that's another concept, as well as been working with Marshall Space Flight Center on a concept for a high-temperature Brayton test cycle that would be used to test like the bimodal concept from a materials point of view. And finally, I wanted to show you that my little filters, and I brought one along here. This one wasn't nuclear tested, so you can handle it. It's a labyrinth design, and so they did, Oak Ridge, who helped me with what's called a DOP test, showed it was 9999, I forget how many nines they had in there, prevented, you know, nothing escaped from it, basically. So that's why it's been used. The company that makes them is Ceramim. I think they're in New York, but they actually are partnered with a company that manufactures them in Denmark. I'd really like to go there again. Just to show you that we can take some of the new technology, just like Stan was saying, and we can duplicate all that testing that was done, and we can do it in a reasonable way and in a controlled way and in a safe way. And the final thing I want to leave you with is the safest national laboratory last year in 2010 was Savannah River National Laboratory. So we want to do it safely. We want to apply the technology like Stan was saying, and we can replicate where we were, and we can go beyond, all the way to Mars. And I guess we'll have questions now?
Sure. I don't know if any of you are aware of Robert Dewar's concept for a nuclear plane. I was curious if any of you had any opinions on his use of the nuclear single stage to orbit as a way to drop the cost to orbit under $100 a kilogram. And secondly, are all these nuclear engines fully on all the time, or do you throttle them by adjusting criticality as opposed to just the hydrogen flow? Can you have designs that are not critical at all times?
No. Let's see. On the single stage to orbit, I think the safety issues are what you're concerned with. We generally have, from a safety point of view, don't want to start a reactor up until you get to a height, which what we call a nuclear safe orbit, which only means that if you have a failure, the reactor will not come into the Earth, excuse me, Earth's environment until the radiation levels are at a safe level. And so, yes, the single stage orbit has been looked at, but has generally been rejected for that reason. It's a safety issue. Let's see, your second question was on the engines. All these engines can be throttled. One of the beauties of a nuclear reactor actually is that you can operate it over something like 10 or 12 decades. If you wanted to, you could throttle it over that amount. Their throttling is actually used during the shutdown process. And the reason is that the disadvantage of a nuclear reactor is when a chemical rocket, you come to the end of operation, you have a nice sharp cutoff, you just stop the pumps, everything stops. A nuclear reactor, you have built-up fission products in the fuel, and so you have to cool it a certain amount afterwards. And so throttling has been used as a method to keep a very high thrust and reduce the amount of coolant required for the afterheat.
Well, yeah, my question was, though, when you bring these nuclear engines down from full power, do you throttle them in the sense of taking them out of criticality, or just throttle them in the sense of putting less and less gas through them?
Well, it's really a two-stage process. The first part, you take them, you throttle them to minimize the aftercooling. The second stage is that once you've done as much as you could, you then essentially scram the reactor,
okay,
shut it down, so you're not generating any additional new after heat.
Okay. So
It's not generating its own.
right. One final question. Did anyone ever think about, try, design, rather than the usual Bell expander, aerospike expanders for nuclear rockets? Anyone ever look at that?
Okay.
And I'm sure that as a further stage in the development, I'm just trying to get by. Yeah, that's a logical question, how much expansion do you need?
Okay, I just want to say Stanton is so understated, but I want you to know that the nuclear rocket really has had a lot of interest, and the Discovery Channel sent 2 groups of film people down to film that area, the Jackass Flats, with Stan, and also Rocketdyne did a lot of the work, so they sent them over there to see that. This is a crew of about 6 or 7 people. And the series was called Mars Rising, and William Shatner was the narrator. So if you ever see it, just know that the interest is out there. Okay, that's all.
Thank you. Very good.
Yeah.
Hi, I've got sort of a practical question. I worked at Savannah River plant 2 years, 2 summers back in the early 80s, so I've always kind of followed what's going on there. And one of the things that happened is they had a big cleanup issue. So has that been taken care of, and what do you feel like the public relations aspect would be of starting a new program there? Do you think you would be getting any flack on that, given that they have had problems there?
I fully expect flack.
One additional thought. There's all this concern by some people that the operation of this nuclear system will produce a radiation environment that will not be tolerated by the people that live around the test development session. In response to that, the technical facts in certain cases are that the more radiation you get, the longer you live. And to make that point, you're looking at a guy right now who got a hell of a lot of radiation, far more than what is considered to be allowable now. And I am 88 years old.
I'm the junior member. I only got 120 gray, and 50 gray will kill you.
A separate issue on, you guys are all talking about fission, and back when you were doing this, fission was obviously much more mature technology. Robert talks a lot about how where we are going to Mars versus where we are going to the moon, how farther we are along. What about fusion? Is there any, are we at a point where we can even think about fusion rockets?
Well, I can talk to that a little bit because Savannah River National Lab is supporting work at the ITER facility, ITER, in Cardache, France. And there are still a lot of fusion challenges that are decades away in development.
Lazard had a fusion rocket concept that evolved over time. But today, there's nothing that brings anything more to the fraction of neutrons per second. A long way off.
Thank you.
That's a good question. I do appreciate it because it's a case of had we, being reflective, but had we continued on 4 decades ago, I think we would have been able to answer that question. Right.
I'm aware that INL has done work with tungsten fuel elements for their NTR work. What sort of work's being done at Savannah River for NTR?
Outside of proposals, and I've been in a lot of discussions with Stan Borowski, who is the program manager for nuclear thermal propulsion. And he informed me that FY12 there is a budget for nuclear thermal propulsion. He knows who I am. INL is also where the remaining NERVA fuel was burned up.
Okay.
So.
Tungsten is certainly a possibility.
Right. Now, one of the University of South Carolina, the department head, Dr. Travis Knight, was working on ternary fuel, and I talk with him on a regular basis. He's in Columbia, which is very close to our site.
I guess on a separate but related question, I understand that tungsten was looked at earlier in the NERVA program, but
it was
not used.
Actually, there was work being done in Cleveland at the Lewis Lab, NASA Lewis Lab, with tungsten. And there still is an interest in tungsten. There's no question about it. Yes. But the thing is, Los Alamos had picked graphite, and that was the one that was further developed, available, and that's where tests were being done. But there was still tungsten work being done at the Lewis Lab.
Okay, thank you.
In Cleveland.
The Saturn parts all seem to be gone, missing, plans gone. Nobody can rebuild it. What about all this NERVA and stuff? Are those plans still around?
Well, that's the sad part of the epilogue. In my laboratory, they hauled off anything I had to the museum, and I'm afraid that's what's happened to a lot of the Saturn equipment. It's been made into museum pieces. So as far as any hardware, usable hardware, I'm not aware of any that's left. The metal pieces were scrapped or buried.
Surely there's some plans somewhere.
It was. At one time, I can't say how it is today, all the reports and plans were stored at Los Alamos. And I don't know whether they're still there. I know the Aerojet work was, reports and such were transferred to Los Alamos for storage.
Right. And I talked to Dr. Stephen Howe in Idaho National Lab a month ago, and he said they recovered 1,900 design drawings towards trying to re-authenticate that under contract to Stan Borowski at NASA Clinton.
So we don't have to rebuild it from scratch?
No.
I don't think so.
It's entirely possible that it will be deteriorated. It won't be maintained.
The quality of those drawings
is... One of the most important things, actually, that you are really losing is the people who knew how to do things. There are people, you can say, here's a plan to make a fuel element, but when you get down to it, there were some people who really understand all the details of it, and I think they're invaluable to go back to.
Yep.
And that's what you're really going to have a hard time.
Absolutely.
There's enough drawings around what the fuel element looks like, et cetera, but it's the detail that you really got to worry about.
And a lot of the materials that we used to regularly work with like the beryllium. I'm a beryllium-associated worker, but it's not easy to get qualified to do that work anymore. So it's changed, but it can be done.
Thank you.
The real thing is it takes the will.
The design and drawings and stuff are more important than the actual parts. But what I come up for is I remember about 46 years ago, I was reading about how we were going to have super cheap, incredible quantities of fusion reaction within that would produce all the power anybody might dream of using within 30 years. And you know, 25 or 30 years, that was 40 some years ago. And yeah, 46 was, and recently I read that we were only 35 years away from this.
Well, that sounds like before Vasimir, but I'm sure that the trend started before Vasimir.
I'd like to ask a question. You summarized what has been done.
Yes.
What is being done right now in terms of funded active programs that bear directly on nuclear propulsion that would help us go to Mars?
Robert, do you know what's being done right now on nuclear thermal propulsion as far as budgeting? Oh, you can tell? Okay.
One point, the reason I can tell is because I just talked to Stan Borowski.
Oh, you did? Okay.
And it happens that the Cleveland lab of NASA is working with the Department of Energy to talk about restoring the reactor capability, examining it, looking at it, thinking in terms of small reactors that could be used in these areas effectively. I just learned that 2 days ago, frankly, when I talked to Stan.
And which lab was this?
The Cleveland Laboratory of NASA, the Cleveland Glenn Research Center.
Right.
I still refer to it as the Lewis Research Center. But when I went there, it was the Aerospace Research Center. And then became the Lewis Research Center.
Okay.
It's the Glenn Research Center.
All right. So
It's a minimal budget,
right.
though.
We're going to have to close it down. By the way, gentlemen, if you could each sign each copy of that poster, because all the plenary speakers are signing that. Yeah, Stan Borowski is carrying on the good fight, and he's trying to get some development work done. But I just have to say, in the absence of a Humans to Mars program, it's almost certain to be aborted.
Very tough.
Unless there's a program, there's no follow-through. And that's the thing. Anyway, that's the end of the panel. Thank you. Dr. Budin has his book, the 3-volume set on space nuclear power propulsion, in the back, and he'd be happy to sign copies that people buy. Thanks a lot. Bye.